Percent composition isn't the only way that we can analyze compounds, though, and it's really, for the longest time, and the least expensive way is to do this combustion analysis. So we have some unknown compound, we'll say CXHYOZ, and then we burn that. And we're going to get out, as our combustion products, is always going to be the oxide, the most stable oxide of whatever's in that compound. So for carbon, that's going to be CO2, and that's going to be water, which is the oxide of hydrogen, is the most stable. That's what's going to come out of it. Remember, there's conservation of mass, which is conservation of particles. So however many atoms of carbon we have here, that's got to end up being the number of carbon atoms over here. And however many hydrogen atoms, that's going to end up being the hydrogen atoms over here. Now, oxygen's not true because we're adding the oxygen because we're burning it. But the carbon and the hydrogen will be conserved. So however many atoms or moles CO2 we get out will become, we can then find out how many atoms of C we have, or moles. Actually, we'll say not atoms, we're going to stay with moles of C. And we can do that same thing with H2O. If we have so many moles of H2O, that's going to lead us to how many moles of H we have in that original compound. Now, we have two. We're going to get out two of these for every, it's H2O, and the other one is CO2. So we're going to have to take that into consideration. But our calculation would start with, in this case, we have 1.10 gram of CO2, and we have 0.676 grams of H2O. Now, we always go to moles. So we're going to multiply by this conversion factor that cancels grams of CO2 and makes this moles of CO2. And that's 44.0 if you add up the molecular weights to get the molecular weight. In this case, water, we're going to cancel grams of H2O for every 1 mole of H2O. And that's going to be, in this case, 18.02 for every 1. And we do that arithmetic, and let's see what we get. So that becomes 0.025 moles of carbon. And for hydrogen, now I misspoke, these are moles of CO2. And then for the water, this becomes 0.375 moles of water. And what we really care now are the moles of carbon and the moles of hydrogen. So that's our next step. Then if we put mole of CO2 down here and put moles of C up here, that's going to be 1-to-1 there. That cancels those units. But this one is not. We're going to put now moles of H2O down here. Every time we have a mole of H2O, I'm out of space there again, this is going to be 2 moles of H. So it's going to be twice that number. So our moles of carbon are going to be equal to 0.025, and our moles of hydrogen are going to be twice that, 0.0, and that I got that wrong too. That is a 0 there, so it's 0.0375. So writing that out, just twice that number, and it's going to be 0.0, there's a point there, 75 moles of hydrogen, and this is moles of carbon. And this asks for the empirical formula, and that empirical formula is going to be the ratio of moles of C to moles of H. So we have 0.025 and we have 0.075. Again, divide by that smallest number to make one of them a 0. And we're going to get out C, let me write it down here, I'm out of space over there, CH3. There's our answer.